The next reaction we'll talk about is a hydrohalogenation reaction of an alkyne. You should recall that hydrohalogenation reactions add a hydrogen and a halogen across a pi bond. In the case of an alkene, we will see a new hydrogen and a new halogen and elimination of our pi bond. You may also recall that when you have a hydrohalogenation reaction of an alkene, you generate the Markovnikov product, where the halogen is found at the more substituted carbon. These same rules apply for reactions with alkynes. If you have a single equivalent of HX with an alkyne, we will generate the Markovnikov product, where we have the halogen appearing at the most substituted carbon. This follows the same mechanism that we discussed with hydrohalogenation previously. The only difference here is if we add an excess of our acid, we can actually generate a geminal haloalkane, which means we have both halogens on the same carbon. How does this work? Let's review the mechanism briefly. If we have a single equivalent of our acid, we will generate the alkene shown above. Now, if we react this alkene with another equivalent of the acid, we will generate a carbocation with the most substituted site right here with the carbocation. Again, the alkene will attack the hydrogen and will kick off this halide here. You might think that because halogens are electron withdrawing that this might actually destabilize the carbocation, but we can actually see a resonance form where one of the lone pairs of the halogens will come down, generate a double bond, and help distribute that positive charge. Finally, the halide will attack the more substituted carbocation here and generate our geminal haloalkane. To summarize, hydrohalogenation reactions with alkynes, just as in the case with alkenes, will generate Markovnikov products. Also, if you use an excess of the acid with these alkyne reactions, we will generate geminal haloalkanes.